G'day viewers. In this segment I'll give you an introduction to the error codes we're going to see to detect and correct errors. Our topic is how to handle the different errors that occur at the physical layer. The problem in essence is that some bits in our messages at the link layer are going to be received in error because of noise at the physical layer. This is unacceptable in that we can't send a message across a network and have a different message arrive at the other side and think that was the real message. You wouldn't be very happy if this happened every time you sent messages across the internet, for example. So we will need some way to handle these errors. There are a few alternatives that we'll look at. It's possible to detect some of these errors using codes. We'll look at this later. It's also possible to correct some of these errors using codes. You'll receive a message and not only realize that something's not quite right with it, but be able to take a good guess about what message was actually sent. And finally, it's possible to, after you've detected maybe that there's a problem, retransmit a message which was in error and has otherwise been lost. We'll look at this option later, and first of all just talk about error codes. These kinds of error codes are a reliability function, and we'll also see as we go through this course that reliability is a concern that cuts across all of the layers. Every layer will generally do its part to improve the reliability of the system. At the link layer, we're mostly concerned with bit errors that might occur and what to do about them. At higher layers, we might be concerned with recovery actions and so forth. Okay, so the problem here is that noise can flip some of the received bits. You can see the signal I sent in above, just one of our good old-fashioned NRZ coded 01 signals. I'm going to draw a slightly noisy version of it. It's a 0, the signal's kind of wandering, and then a 1, and then a 1. A few zeros, and a 1. But you can still make it out. On the other hand, if the line has been long and the signal is very attenuated relative to the noise, we might have something that's much more messed up. What is this? Well, this looks like 0, 1, 1, 0. I don't know what this is. This could be a 0 or it could be a 1. Maybe that's a 0, 0. I don't know what this one is either. Let me make that even a little more messy, just so it's clear that there's a lack of clarity there. In this case, we may end up making decoding errors and think that we got a 1 here when we received a 0, or vice versa. These are the errors that we would like to handle. Observe that in our case, in this scenario, the receiver maybe doesn't even know there are errors. It's just got the bits, it's decoded them. Some of them might be bad, it doesn't know that yet. How are we going to deal with these errors? To handle them, what we will need to do is add structure to the message by adding some redundancy. Only by adding some kind of redundancy and structure will we be able to recognize that the message doesn't look quite right, that something is wrong with it. With error detection codes, we add a little bit of structure in the form of check bits. We add these check bits to the message, and these check bits will then let us detect an error at the receiver, when an error has occurred. On the other hand, we could pursue error correction codes. In these schemes, we'll add check bits also, but usually more check bits, so that not at the other side we can look at the structure of the message, see that something's wrong, and take a good guess as to what the message was, and thereby correcting some of the errors. The key issue for us is how we're actually going to do this. It sounds kind of hard. This is actually a very interesting topic, don't you think? How are we going to structure these messages with codes so that we can solve this problem? Not only that, but for a good code, we would like the code to be able to detect lots of different kinds of errors, not just single-bit errors, but maybe situations when 2-bit errors occur in a packet, and so forth. We'd also like to do this with few check bits. Every time we send a check bit, we're using the channel for something other than the real data we care about, so we're adding more overhead, so don't use too many of them. We'd also like to do this with a scheme that involves only modest computation at the sender and receiver, if we can. We're generally willing to use a bit of computation will really help, but this is computation that has to go on, at line rate at the sender and receiver, so it's adding complexity to the system. To warm up to some of these codes, we'll start with a motivating example. So here's a simple code that we could use to handle errors. Got a brilliant idea? You ready for it? Here it is. Send 2 copies. It's just an error if they're different. I hope no one's patented that.
Okay, so here's our example. Here is the message, 010, and we're simply going to send another copy. We'll send it again, back to back, 010. Great. Actually, let's not rush out and patent it before we think about how good this code is. First, we could ask, well, how many errors will it detect or correct? The number of errors it can correct is 0. It can't correct anything. Suppose, for instance, that we had received a 1 on the very end instead of a 0. Well, now you can see these two things don't match, so we know something's wrong, but you don't know which bit is in error, that this one was flipped rather than this one. You just know there's a problem with some of them. How many errors can it detect? Well, I don't know. I guess it could detect up to 3 errors if there were errors in different bit positions. But here's the key issue. The key issue is not how many errors it could detect in the for very errored messages, but rather the minimum number of errors which are required, which are able to make the code fail. Suppose that I also flip this same bit in the same position. They match. Our check will say there's no errors. But all I've done is added 2 errors. With 2 errors, this code can fail. So it's not a very good code, really. Not only that, I guess, but to get that level of protection, I spent 50% of my link on overhead for error detection. And I didn't really get a lot of error detection out of it. 2 lousy bit errors, and the scheme could fail and tell me I've got a message that's right, when in fact it's wrong. So we want to be able to do better than this. We want to be able to handle more errors with less overhead. We're going to look at some real codes which are used to do this, that can detect and correct errors in stronger ways than that motivating example. These codes are basically going to be different kinds of applied mathematics. In general, you won't go out and invent a new code. You'll look one up and you'll use some well-known existing codes which have been checked and debugged, which have been optimized by mathematicians, essentially. These different codes, though, they won't be able to handle all errors. All of the codes are built to handle some level of errors, not an arbitrary level of errors. It can't be done. And it's also the case that these codes focus on accidental kinds of errors, rather than malicious errors, as might occur when an adversary is trying to trick you. It is possible to come up with error detection schemes which work for malicious traffic. These are called secure hashes. This is a cryptography subject, and we'll probably mention them briefly when we get to security at the end of the course. But right now I'm just focused on regular error detection and correction codes for errors in the physical layer. To use error codes, just diving into the next level of detail, here's the overall structure. We're going to send code words. A code word is going to consist of the D data bits. That's actually the message bits that we want to send. And then to that we're going to add these check bits we talked about, R different check bits. There is a vast literature on error codes. And the kinds of codes I'm going to talk to you about, just so you know, they're called systematic block codes. Block codes mean they operate on a block of bits at a time. Systematic means you append the check bits rather than rewrite all of the data bits. Those terms will help you if you're trying to read other literature and see where these schemes fit in. The way the codes will be used at the sender is that the sender will be given the data bits D from the higher layer, and it will then compute the check bits. The check bits here are strictly a function of the data, so they're computed by a little routine as a function of the data. We'll then append them and you send them into the network towards the receiver, and you're away. The sender has done its job. On the other side, the receiver will receive from the network this package of D plus R bits. There could be errors in this bit, in these bits. Let's just say there's an error in the data here. Maybe I'll do an X in the data here. What the receiver will do is it will take the data bits and it will recompute the check bits from that data. R there is a function of the D data bits, and it will see if they match the R dash bits that it received. They should match. If they were both computed from the same data, they should match if everything's okay. If they don't match, then it's an error. In the case where I put an X here, we will get an error because our R should be, hopefully, we've got a good code different from our R dash. Observe that one thing that's difficult about the codes here
is that the error could also be in the check bits. Suppose actually my data was fine and the error is in my check bits. This procedure will still tell me there's an error. There is. Not an error I really care about because my data bits are okay, but I have no way of knowing that, simply that there's an error somewhere in the D+R bits. And that's because the bits that go over the physical layer don't distinguish check bits from data bits. The check bits are not magical, they're sent over the channel, and so they're subject to errors just as much as the data bits. This is what makes error codes very tricky and interesting to look at. Here's a little more intuition as we think about how to design some of our codes. Okay, we have D data bits and R check bits. In this picture, I'm trying to draw just the space of some of these different designs. If we look at all of the code words, how many code words are there? Well, a code word is D plus R check bits. So there are 2 to the D plus R different possible code words that could be sent and received. Actually, that could be received on the other side. There are 2 to the D plus R possible incoming sequences of D plus R bits. But actually the code words, the really correct code words that get sent, how many of them are there? Well, we know that they're D plus R bits long, but there are only actually 2 to the D different bits because the R bits are computed as a function of the data. So there are only 2 to the D possibilities. Well, that means if I randomly pick a code word from this space, anywhere from this space, it's quite unlikely to be correct. In fact, the chances of it being correct would be something like 1 over 2 to the R. That's what you get when you take 2 to the D and you divide it by 2 to the D plus R. 1 over 2 to the R gets fairly small as R gets large. If you have a 16 check bits, for instance, you've got a 1 in 65,000 chance of accidentally picking a code word. What we would like to do when we design code words is make it so that errors essentially make it likely that we will pull a random sequence of bits out of this space that will not be a valid code word. Then we'll be able to work out that something's gone wrong and try and correct it. Much of the early work in this space was done by Richard Hamming. He was a pioneer of some of the early codes. There's actually a very nice paper he wrote in the 1950s. This one, Error Detecting and Correcting Codes. You can look for this web and read it. This paper on the web and read it. It's really very readable and it develops in a very elegant way something called Hamming codes, which we'll look at. Hamming did all sorts of work on codes and other things. He was one of the great early pioneers. You could also find on the web a talk he gave on You and Your Research, which is part motivational and advice that's often quoted. Okay, so here are some of the concepts that Hamming came up with, which we need to know to work with error codes. He came up with a concept of the Hamming distance. The distance by itself is the number of bit flips you need to change. It says D1 to D2. This should really be full code words. D plus R1 to D plus R2. Whoops. Now, let me give you an example of a code. Suppose when we have a data bit of 1, I'm going to send 111. Triple repetition code. Just send the same data 3 times. Seems good. Got to be better than sending it twice. For a 0, I'm going to send, you guessed it, 0, 0, 0. What is the distance? So this is the complete code set here. That we just 0 and 1 are the only messages. So 111 and 000 are the only code words, valid code words, which could be sent. Of course, any sequence of 3 bits could be received. What's the distance between these 2 code words? The distance is the number of bit flips to turn one of these into the other. So it's 3. We need 3 bit flips. Now the Hamming distance of a code is the minimum distance between any pair of code words that are in the code. In this code, there's only one pair of code words. The code word for 1 and the code word for 0. The distance is 3, so the Hamming distance of this whole code is also 3. Seems fairly simple so far, but we'll use it in just a moment. Okay, so one of Hamming's results was that if you want to do error detection, if you have a code whose distance is D plus 1, then it is able to detect up to D errors always. That many errors, if they occur, you are guaranteed to be able to detect it. Let's see an example. For the code I just looked at, we have d plus 1 is equal to 3. Therefore, you guessed it, d is equal to 2. So that says with my triple repetition code, I should be able to detect up to 2 errors. Here were the 2 code symbols that are valid that we could send, the 2 code words. Let's just write down what you can get if you make 2-bit errors. Well, I could get 001. Yeah, that's an error because that's none of those things. We haven't changed one into the other. I could get 010. I could get 100. I could get 011. I could get 101 or 110. That's all I can get by flipping 2-bit flips from any one of these things. And none of these are valid code words, so I'll always be able to detect it. Of course, if I make 3-bit flips, I can change one of these valid code words into another valid code word, and I won't be able to detect that. But with only 2-bit flips, I will. Here is another of Hamming's result, and this is for error correction. The result here is that if I have a code of distance 2d plus 1, then up to d errors can be corrected by mapping them to the closest code word. If we assume that that there are few enough errors, then that can be done. Let's give an example again. Here we have the Hamming distance. It's 3 for the code, so that was 2d plus 1 is equal to 3. D is equal to, you guessed it, 1. This means we should be able to detect up to we should be able to correct up to 1 error unambiguously with our triple repetition code. Let me write down just an example error. 010. That's the sort of thing you could get as an error. What should we map it to? I think we would map that to 000. Now, if there's only been 1 error, it had to be this, not 111. What if we got 110? Well, we could correct that if we knew that there was only up to 1 error to 111. That's the code word to which it is unambiguously closest. So that's what must have been sent if only up to 1 error had occurred. If more than 1 error can occur in this scheme, all bets are off. If 2 errors had occurred, then this code word, the second received sequence could have actually been all zeros. But this is why with Hamming's bound, this error correction code is only good for circumstances in which there can be up to a single error.